Hi everyone. So this is Unit 3, Lesson 2, Properties of Quadrilaterals. I've taken all of the examples from this lesson from your textbook, which you're hopefully getting more familiar with by this time if you haven't already. I'm only going to give you a couple of examples because, well, as you're going to see in a moment, this lesson is very similar to the last one on triangles. You're going to get some terminology, some vocabulary, and then you're going to have to apply all the tools, slope, endpoint, midpoint, distance, all that stuff, to solve some problems. In this case, we're going to be looking at quadrilaterals, which are shapes that have four sides. So instead of triangles with three sides, we're looking at four-sided figures. And you're going to have to classify them, like what type of quadrilateral you have. Can you prove that you have that kind of quadrilateral using these sorts of things: slope, midpoint, distance, and equations of lines. Okay, so let's get through the terminology, talk about some of the tools that you can use, and go through a couple of examples. Like we said, a quadrilateral is any shape with four sides. So this is kind of an irregularly shaped quadrilateral. It's not really a special quadrilateral as far as having any special name to it or anything like that. It looks a bit like a trapezoid if you know that shape name, except a trapezoid, the top and the bottom would be parallel, which doesn't look to be the case here. Okay, a square is a type of quadrilateral. Should be pretty familiar with this, I imagine, right? So all the sides of a square are the same, and all angles are 90 degrees. So in other words, if you want to prove something is a square, you have to show that all of the sides are the same, and you can use the distance formula to do that, right? All sides are the same length. And you need to show that the angles are 90-degree angles. And you can do that by finding the slopes of these various lines. So if you were to find the slope of this side, the slope of this line, and the slope of that side, you should hopefully know that because this is 90 degrees, the slope here and the slope there should be negative reciprocals of one another. All right, so that's how you can show that something is a square, and you may need to do that. Rectangles. So these are quadrilaterals where all sides intersect at 90 degrees, but obviously, unlike a square, not all the sides have the same length. The opposite sides will have the same length. So the left side and the right side will have the same length, and the top and the bottom will have the same length. But the left side and the top, for example, don't have to have the same length. Okay? So what you can do is show that all of the sides intersect at 90 degrees. If you can show that every side intersects at 90 degrees, you've proven it's a rectangle. Because if this side, for example, was longer than this side, if it came down a bit, well, then you can see that this line here would have to go at an angle. And so you wouldn't have 90 degrees. So if you can show that, yes, all of the points on a four-sided figure intersect at 90 degrees, then you've shown that you have a rectangle. And all squares are rectangles, right? So to prove something is a rectangle is easier. To prove something is a square, you specifically have to show that all these sides are the same length. A rhombus. So a rhombus is a quadrilateral where all sides are the same length. So if you want to prove something is a rhombus, you're looking at proving that all sides are the same length. But the angles are not necessarily 90 degrees. A square is also a type of rhombus where these angles are 90 degrees, but for most rhombuses, the angles here will be something different. Okay, so all you got to do to prove something is rhombus is show that all four sides are the same length. Finally, the last shape that we're going to look at is a parallelogram, and this is a shape where both pairs of sides are parallel. So for example, AB is parallel to DC, and AD is parallel to BC. So this pair is parallel to each other, these two are parallel to each other. And you should hopefully know how to prove that, right? If you have the equation of AB and the equation of DC, their slope should be the same, right? Same slope because they're parallel. Same thing with AD and BC. So the angles here can vary, and the side lengths are not always the same. Although these two sides and these two sides, like a rectangle, these two sides and these two sides will be the same. Okay, so think about if you're having to prove that a shape is one of these things, think about their attributes. You can prove it usually by finding distances, by finding if they intersect at 90 degrees, right? By finding equations of lines and finding parallels. finding the negative reciprocals of the slopes and seeing if they match up, or for parallelograms, seeing if they have the same slope. So those are generally the ideas that you're going to be working with. There are a couple more shapes that are normally covered in grade 10, which I'll mention here. There's a kite shape, and there's a trapezoid. Because we don't have time, we're just going to be skipping those and focusing on sort of these core main shapes. Okay, let's do a problem here. So again, this is from your textbook. We have this picture here, and we want to verify that quadrilateral EGF, so that's the light blue here, EFGH rather, the light blue here. We want to verify that this quadrilateral is a parallelogram. So we're trying to prove that EFGH is a parallelogram. It does kind of look like one. So remember, how are we going to do that? Well, what we can do is we can find the equation of this side and the equation of this side and see if their slopes match. Well, we don't even actually need to find the full equation. We could just find the slopes. Same thing for these two. We want to find that their slopes match. All right, so this problem is a little bit trickier because we don't actually have any of these points. We don't have E, we don't have F, we don't have G, we don't have H. But we are told that these are the midpoints of A, B, C, D, right? So point E here would be the midpoint between A and B. So first step is going to have to be finding all four of these points. So like we said, the E is a midpoint between A and B. So we're just going to use the midpoint formula. So we can get our point here as -1, -1.5, right? x2, x1, x2, y1, y2. So that's just these 2 points that you're subbing into that formula, right? So you can see there's x1, there's x2, there's y1, there's y2, all plugged in, and we get our midpoint. We do the same thing for F, G, and H. So for F, we have our midpoint 4.5, -4, so that's the midpoint between B and C. G is the midpoint between C and D, and then finally H is the midpoint between A and D. Okay, so we've got all four midpoints. Well, now the problem is actually fairly easy because if you have all these points, say I have E, F, G, and H, well, I'm again trying to find the slopes of all these lines to see if they're the same, right? To see if the slope of HE and the slope of GF match, and the slope of EF and HG, see if those match. So slopes are pretty easy if you've got 2 points, right? If you have 2 points, then we can just use the slope formula. So we're going to find the slope of EF. Since I now have point E, -1, -1.5, and I now have point F, 4.5 and -4, I can have my y2, y1, x2, x1. Did I order that correctly? Yes, I did. You could do it the other way around, it would still work. And so I plug those into the formula, and I get a slope of -5/11 for MEF, for the slope of EF. Okay, I'm going to do the same thing for all the rest of the lines. So for FG, so again, I have my point for F right there. It's the midpoint. I found another midpoint here, G. I take those 2 points and I plug them into the formula, and I end up with a slope of -10. So if you want, you can go through that calculation. I won't go through that any further. I find GH, the slope. So again, I have point G and I have point H. I find the slope there. And I get a slope equal to -5/11, which is promising, right? Because this is -5/11. If that's -5/11, then I know that EF and GH are parallel. They have the same slope. All right, FG and HE. So I still haven't found HE. So HE, I'm going to have point H and point E. So there's point H and there's point E. I'm going to get the slope. And I get -10. So I can clearly see that that's the same as this, and I now have all the information I need to prove that this is a parallelogram. But we do need that final statement to prove it. So we can say, yes, this is a parallelogram because these two sides, EF and GH, have the same slope. So these two sides are therefore parallel, and the other two sides, FG has a slope of -10, HE has a slope of -10. Because they have the same slope, those two sides are parallel. So in other words, we have a shape that has 2 pairs of parallel sides, so this is a parallelogram. Okay? Not as long as some of the questions we did in the last section, but still, you have to know what you're doing here. All right, we're going to go through a second example. Verify that the quadrilateral with vertices at P3, 3, Q0, 1, R3, -1, and S6, 1. We want to verify that this is a rhombus. And then we're going to do something with diagonals that I'll talk about after we solve for part A. All right, so part A, we have a diagram of it down here with the light blue lines, which are for part B, and we'll ignore those for now. But again, you want to draw a picture of this before you try to do anything here. But remember that a rhombus, right? A rhombus, if we go back up here, a rhombus is a quadrilateral where all sides are the same length. So if you want to prove something is a rhombus, it's very easy. Just show that all sides are the same length. Now you might be wondering, well wait, if all sides are the same lengths, couldn't it also be a square? And your answer is yes, but remember that a square is a special type of rhombus. It's a rhombus where all these angles are 90 degrees. So if you've proven all the sides are the same, you've already proven it's a rhombus. You don't need to do any more work. If you want to prove if it's a square or not, then you would find these angles. You would see if they are 90 degrees or not by using your perpendicular slopes, right? But we're not asked to do that. We're just asked to find, is it a rhombus? So there's no point in doing more work than we need to do. Let's just find if all four sides are the same. Okay, so that's pretty easy because we have these points. So all we got to do is use the distance formula. Now again, this is where drawing your figure is going to be really useful, because if you're trying to find the distances between these points, it can get easy to get mixed up if you don't draw the picture, right? If you find PQ, well then what do you also have to find? PR, I guess? PS, QR, QS? What do you have to find, right? It's a little confusing. But if you diagram it out and label all your points, then it becomes very obvious. Okay, I got to find PQ. I got to find QR. I got to find RS. I got to find PS. Very easy, right? Draw that picture. It'll save you a big headache, even if it takes you a little bit more time at the beginning of the question. All right, so that's all we've done here. We've just found the lengths of each of these sides using the distance formula. So PQ, again, if we look at our picture, I may have said PQ, I may have said QP. It doesn't matter. Either they both have the same length, right? It doesn't matter where you start and where you end. So if you go QP or PQ, you'll get the same answer. So we have our, this might be x2 or x1. Again, it doesn't matter as long as you're consistent. That would be the other x. So if this is x2, this would be x1, y2, and y1. Plug them into the formula, and you end up with the root of 13 as this length of PQ. You do that for the other sides, PS, SR, QR, and you find that they're all root 13 when you sub in those points. So that tells you that all sides are the same length, so therefore PQRS must be a rhombus. And you've solved part A. Part B. Verify the diagonals of PQRS bisect each other at right angles. All right, let's be a little bit careful with this. So what do we mean by diagonals? So diagonal in this case doesn't necessarily mean that the line itself is diagonal on a graph. What it means is if you look at your rhombus, a diagonal is defined as the line that goes from a point on one side of the quadrilateral to the point on the opposite side. Okay, so in this case your diagonal is a horizontal line, it's a straight line. But we call it a diagonal because it's not one of the lines on the outside of the figure, right? It's if you were to flip this so that this line was horizontal, then this line would become diagonal. So it's basically, just think of a diagonal, just keep it simple, is a line from a quadrilateral that connects one point to the point on the opposite side. Okay, so we want to, what do we want to do again? We want to show that the diagonals bisect each other at right angles. And there's a few ways to do this. So you might think of a completely different way from what we've used in this question. So you don't have to do it this way, but we're trying to show that if I connect Q to the opposite side S and I create a diagonal, and I connect R to the opposite side P and I create a diagonal, that they intersect, that they bisect each other at right angles. So I need to show that this is, that this point of intersection is exactly in the middle of these two lines, and I need to show that this point of intersection creates a 90-degree angle. So that's what I'm trying to show here. Okay. Now keep in mind that there are two diagonals for a rhombus, right? All quadrilaterals have two diagonals because every point will have only one opposite point, right? If you have a four-sided figure, then two of the points must be next to one point, so there's only one other point it can be opposite to. Okay, so what we're going to do here is we're going to say that, well, if this line intersects this line, if they bisect each other, meaning they connect exactly in the middle, then this point of intersection here should be the midpoint for both lines, right? It should be the midpoint for QS, and it should be the midpoint for PR. Because if they didn't bisect each other, let's say, I don't know, this line was somewhere here, then that would mean that it cuts this line somewhere not in the middle, right? If they bisect each other, then they must connect right in the middle of one another. They must have the same midpoint. They both have the same middle. So that's pretty easy to calculate, right? So the midpoint, we just find the midpoint of QS, which we've done here. We find the midpoint of PR, which we've done here. And yes, it turns out that they have the same midpoint. So that means that the point where they touch is the middle of both lines. So we can say, yes, they bisect each other, meaning they cut each other exactly in half. Okay, now all I've proven is that the diagonals bisect each other, but I have to prove that that is at right angles. So all I got to do is find the slopes of these two lines. If the slopes are negative reciprocals of one another, then they will turn out to have a 90-degree angle, right? They will be perpendicular to each other. So the slope here for the lines, we just use the slope equation, y2 minus y1 over x2 minus x1, pretty basic. We sub in for QS, points from Q, points from S, so this would be y2, this would be y1, x2, x1, and we end up with a slope of 0. Which we would expect, because a slope of 0 will be for a horizontal line. This line looks horizontal. Okay, so if this line is horizontal and it has a slope of 0, then that must mean that PR is a vertical line. And let's see if you can remember, what is the slope of a vertical line, right? Slope of a vertical line is undefined, so it means that you're going to get some number over 0, and then you can't divide it. So let's see if that happens. We sub in points P and we sub in points R to the slope formula. So we get negative 1 minus 3 over 3 minus 3. So yes, we do actually get a 0 on the bottom, so this is undefined. So we know that this line is vertical, this line is horizontal, so they do intersect at 90 degrees. Okay, so now we've proven that these two lines, QS and PR, intersect each other at 90 degrees, and their point of intersection is directly in the middle, so they bisect each other. Okay, so we can say in a statement, therefore PR and QS bisect each other at right angles. Okay, so those are the only two examples I'm going to cover here. Again, there are a lot more examples I could have gone over, but they all involve taking knowledge of the properties of these parallelograms and basically checking these properties using this stuff. So it's going to take a bit of practice. So please try out a few questions to make sure that you're prepared for the assignment that you're going to have at the end of this unit. All right, that's it. Thank you.